Good morning, everyone. Welcome to this session to CptS 317 on this Friday, April 17. It's 10:10 here in Pullman, and I'm sure it's the same time for most of you, but there will be some people who are somewhere else where the time might be different. Happy Friday. We are going to get started, and I will continue the discussion we started this week on a relatively big topic on reducibility, and that will be part 3. We did do part 1 and part 2 on Monday and Wednesday, and so we'll continue with this discussion today, and we will get to our warm-up question, but I want to delay it a little bit today, so because I've got an exciting thing to share, and so once I tell you about that, and before we get to our topic, that will be the time for you to get to your warm-up questions, and there will be a natural point where we will kind of link up that topic on what we will do today and what I would like to ask you. And so the reason I am excited today to start right away is because we have finished grading midterm 2 and it is back, and that is a good reason for celebration, and that would be the first thing I wanted to report. And before we get to with our topic, I want to report on that one. And the other thing that I'm excited about is that it's not just that we finished grading, which is an accomplishment and something that I promised we will try to do by today when we talked about this one last time, but also the class did well. And so I wanted to take a little bit of a moment to talk about that, tell you where you are, and then we will get to discuss other things. So we've got two great things around this midterm: the fact that it is graded and back to you, and the fact that you have done well. By back to you, I mean you have got responses on Oswald. So if you go there, and it was published like 5-10 minutes before this session started now. So it is, if you are eager, very eager, you can, this will be a time where you'll be excused to pick on what feedback you got there. If you want to wait, then that will be perfectly fine too. But I want to talk about what the exam was like and how you did, and why I am excited that it became a good result. Here is what your grade distribution looks like, or the points that you have found. And I tried to make this one easy so that you've got intervals of 5 points each. So there are people who've got perfect score, 100 and to 96 is one group, and then it goes on like down the road. And so if you look at this, you should have good reason for celebration as a class and individually also. And so a good portion of you have done extremely well, and there are some who have done well, and there are some who need some improvements in some ways. The grading itself was careful, just like Santa would do on a list and check it twice and so on. We did do that. James did a great job looking at things, and I did check things. And so there were at least a pair of eyes that saw it in terms of what you got. And there are some places where there is some kind of concise but useful feedback you got on each of those questions. So make sure that if you got great points and there was no reductions and things like that, then that's perfectly fine. If there is a place where something was not perfectly right, then that feedback is going to be useful. So make sure that you go there and look at them. And so the overall comment I want to say is I have been happy with how the class did. I have been happy with how you handled a take-home exam. Most of you did this the way I kind of advised you, and some of you used the extra time that you needed on that Saturday, and so it was on a weekend. So, but I have assumed that you will do your job, and from all the indications I have, there is no other thing for me to feel otherwise. And so I congratulate you on having done a great job. I congratulate you on showing that you can handle this sort of things and benefit from the exam itself in terms of learning, and help me assess you in a good way. And so for that reason, I think this was a happy moment. There is a number of ways you can congratulate yourself. If you are the kind of person who would like to get an ice cream because you've done a good job, this is a good time to do that. So make sure that you get your ice cream today, whether it's you go out or you secure it any other way. If you are the kind of person who would like to get a drink and have a beverage of some kind, that will be another good reason. So it is a Friday, you deserve it, you've done a great job. I am happy with how the grades have been distributed and what you have done. What I want to do a little bit of the time now is to actually go back and look at what the exam was and the kind of comments you got, and especially on things that probably would need a little bit of attention and the kind of things that we observed. And so kudos to James for having done a great job helping out and giving you feedbacks that are precise and help with the grading. And I want to take a moment and just reflect on what the questions were and make some observations on the kind of things we saw on solutions. So the first thing is, just like I would give yourselves a chance to celebrate by having an ice cream or a drink today, I should be congratulated on having to fit the exact of the entire exam prompt on half of this slide. So what you see on this slide is the questions repeated again. Of course, it's not all the details, but I managed to get them on one slide, and I struggled, and then I finally managed, and I was very, very happy. So we had 4 problems. Problem 1 and 3 were 30% each, problem 2 and 4 were 20% each, and there they are. And so here's what the questions were. So I want us to have this one on one end and some of the observations we made and the kind of feedback you received on the left space now, the thing that I will start to unpack. So problem 1 was on context-free grammars. Problem 2 was on turning context-free grammars into push-down automata, and that's where James's famous simplified Lisp language shows up. And so we have context-free grammars and context-free grammars and their convergence to PDA. That was the subject matter of problem 1 and 2. Problem 3 was on Turing machines, and that had asked you to give an implementation level description for 2 different decision languages. One of them was going to look for a string that contains twice as many falses as there are truths, Fs and Ts. They could have been anything else, but we chose them to be Fs and Ts. And the other one says it does not contain twice as many Fs and Ts. And so there were some creative solutions on how you would interpret when there is empty, but otherwise the question was fairly well understood by many, and you have responded in a good way. The last problem had to do with chapter 4 of the book that was about decidable. And so there was a specific language that you were given, A in this case, that takes a regular expression describing a language containing at least one string W that has 0, 0, 0 as a substring. These were the 4 problems. Here was how they were. And let me try to tell you the kind of observations we made and how you came across. Now we are on the left hemisphere. And everything that you see here will be either point out how things turned out or things where mistakes were observed. Problem 1 was a place where the vast majority of the class had totally got it right. And so you nailed this problem. So this was language, it was a grammar of English and a simplified version. And you were asked in the first part of the problem to show that this grammar has 2 leftmost derivations for a particular sentence, which means it was ambiguous. That was part A. Part B was to find a rule that you need to remove from that grammar so that you make it unambiguous. And C was to make you apply what you have done in B to remove that rule and show that this sentence that came as a result was going to have only 1 derivation. The sentence you worked with were creatively designed to be current. And so for A, you had this sentence that says the students wash their hands with soap. And almost all of the class, I should say, except for very, very few, did get that derivation quite right. There was quite laborious things to do, and I applaud you for having to be patiently writing that out. That was also a question of patience. It was not just a question of getting it right. And some of you threw parse trees, but you did that very well. And so it was good that you have understood that and you demonstrated that and you applied on a sentence that I think is also true of how you're practicing. The students wash their hands with soap. On the second part, there is more than one way in which that grammar, that is a very lengthy one of English, could be fixed so that that ambiguity could be removed. Most of you identified the one that came first to our minds, and then there were some who found another one. So there are multiple. It's not just one, but there are multiple of them. For those of you who had gotten one or the other, we have given full credits because that's exactly what it should be. There were very few people who went a little bit ahead or more than what was asked. We said, remove one rule, fix this grammar to be ambiguous. And so whatever additional thing you have done might have changed the intent of the question. And so you might have got subtracted a point or two there. That's not a big deal, but that's how it was graded. The last one was to show on another sentence after this fix is made that it is not going to be ambiguous anymore. And that sentence was that said, the students take their classes via online delivery, and that had only one leftmost derivation, and you did get that one. Problem one, majority nailed it. Problem two is where James shows up with his Lisp, and we've seen this language again and again, and so this was a place where there were some frequently made mistakes. If you want to send me a text message now, you know what FMM stands for. It stands for frequently made mistake. And so there were some frequently made mistakes, and these were among them. You forgot, a good number of you, to read from input, or you have forgotten to handle the parentheses, the left and right, which is important to that language. And the even more common was that you forgot to push in the reverse order, which is what the PDA would do. You will know them when you see that feedback, but that's the place where we saw. So compared to problem one, problem two were some places where some of the class did get points. When you don't get full point, most likely it's on problem two. And then I'll come back to other place where it is common. But that's how you came across. Problem three was on Turing machine. Overall, my assessment is that you did a fine job, but because it asked for implementation level description, there was a lot of variation between how much you actually cared to go into implementation level detail. Our interpretation of it was a bit loose. If you have given enough of a detail, then we call it implementation level detail. But there were some where it really was missing. And so there may be some places where you could improve things. And that's what the comments you got would say. Problem four was undecidable one. So problems 1, 2, 3, you did get a chance to practice with homeworks before that. This one was the one that was newest, and it showed. And so there were some, generally speaking, the majority struggled with having a good way to show this one. And the most common mistake made there was that you didn't technically pay very good attention to how the language A was described. So R is all the input there is. That's a regular expression. And there was additional information that was given that it's describing a language containing at least one string W, and that string has this 000 as a substring. And there were a number of you who did take W as if it was part of the input and you gave. And so one could be even more strict in the kind of reductions we did, but you got reduced pointers on that one. This is how you came across. Here is how you were take it, both to celebrate the good job you have done, but also to learn from the feedbacks that you have gotten now. That was what I wanted to say, and I'm going to continue, and I have not forgotten my word that I'm going to invite your input on, or my question for the day, my warm-up question, my delayed warm-up question will come, but let me put up this slide. Okay, I admit this is a slide that you saw last time. We spent 15 minutes talking about it, but I have to bring it back again just to help you, remind you. We did get homework out on Wednesday. We celebrated that one because we've got a number of reasons. And one of the reasons is that you got some extra days to work on it. And so the deadline is a week from today. It's a Friday, but it was out. And I have talked about the problems. I'm not going to repeat that. It was a lot of time spent last time, and it was with good intention. But I want to have this one up and report on what you told me on the warm-up question we had last time. Problem 6 is about Magic the Gathering. You have a serious thing to do there on a paper that you would read and answer some questions and things like that. But we use this as an excuse to know what we like as a game to play, and I have the top 5. So if you have seen the Oswald post I sent afterwards, you would know how you rank it. But I picked the top 5, and so poker with 20% was the number 1. Number 2 was BS with 11%, and then there was a tie between 3 games for 3rd place. And Magic the Gathering, at least James should get some comfort in it, was tied with Dominion and Dungeons and Dragons for 3rd place, each of these 3 at 8% each. That was the report on last week's warm-up question. Okay, I'm going to have this slide up before we get to our topic for today. Here comes my warm-up question for the day. And so we have done an excellent job on your students wash their hands with soap and they're staying at home. and doing everything that they're supposed to do at this point. But every now and then, I think it would be a good idea to go out for a walk. And so I want to know, I don't go out for a walk, fresh air, that is, often these days, maybe once every other day or something. That's probably what I do. But I want to know, generally speaking, if you take a week as a unit, how often do you go out for a walk? So let me define, because we are very precise in defining things, let me define what walk is. So walk, you could, if you are inside the home and you go from one place to another to fix something, to get your coffee and so on, Fitbit would call it a walk. Let's not call that walk. I mean like going out. Okay, that's out. And then I am going to ask you how long. 10 minutes. If you walk for 10 minutes, then we call it a walk. If it's less than that, we will not. If you jog, perfect, that's great. But anything that makes you go out is what I'm looking for. So in this stay-at-home situation now, how often do you go out for a walk in a week? Every day, twice a week, 3 times a week, or something like that? Just tell me. So go ahead and start doing that. And I'm going to leave this slide up while you guys respond on that one, and then I'll start with the topic of the day. So this will be up for 30 seconds, 45 seconds or so, until I see enough people respond. And if you have not done that, this is also a good time to go to Ausbol and see what feedback you got on midterm 2. Okay. So we've got another 28 seconds left for participating in today's warm-up question, delayed warm-up questions for the day. Okay, it's getting quieter there, so take your time. If you need to calculate how many times you're actually going out for a walk, that's fine. I'm going to allow, my voice, I think, is good enough. I was trying to raise the volume a little bit, but I think this is long enough. Okay, I'm going to get to the topic, to subject matter for the day. And so we have been busy this week doing reductions or seeing reducibility for having to show when problem is undecidable. Our midterm and the things that we have been doing so far, including homework 7, fortunately is, or by nature, has been primarily about decidable problems. And so the last topic we had was on first acknowledging that there are some problems that are undecidable, and then growing this list that we are learning now about problems that are undecidable using a powerful technique called reduction. So ATM, we saw using the diagonalization, we kind of found one problem that we don't need to reduce from. We actually can't reduce from any problem if we don't have anything. So there, at least we had a beginning. The acceptance problem when a Turing machine is undecidable, and we showed that through a technique called diagonalization. And then once we have that, we use reduce problem A to reduce to problem B, and use the solution from problem B to solve problem A. And if A happens to be an undecidable problem, and we show that it can be reduced to this new problem, then the new problem it is reduced to do would be undecidable. Also, because by contradiction, if this was decidable, we can go back and solve the original problem that we reduced it from. And that kind of contradiction is our idea for having to prove something is undecidable. And so we started growing. And I told you last time, we go out in the forest and say, here is a tree, decidable. Here is another tree, undecidable. Here is a third tree, decidable, and so on. If we were to do that, I told you my gut feeling that we may have more of these ones, the decidable ones, but there may be enough. And so now we are growing. They're growing, and we are going to be seeing even a couple more today. So we saw the Holt TM problem, the ETM problem, EQTM problem. These were all undecidable. And for each one of these, we did, except for EQM, if you remember, we actually reduced it from ATM, but for one of them, for EQTM, we reduced it from something else that we have already shown to be undecidable, that was ETM. And we looked at a problem called regular, that was a property of a language, and we showed that also by reduction from ATM to be undecidable, and then we invoked. We didn't go to too much detail, but there are some other languages that we could have also shown using similar ideas to be undecidable. And so this was the world we left last time. And so we looked at this, and then I started talking about something that would be useful for showing even more now undecidable in this general idea of having to reduce one problem to another. Start from an undecidable problem, reduce it to the problem that we are investigating, and therefore show that the problem that we have reduced to is also undecidable, because if it were, the original one would have been decidable, and therefore contradiction comes. And so in this idea of having to reduce, the point we made last time, and I admit last time many of you said there were a little too many things, so we'll not have too much today, but we'll have enough to finish on time and on also finish this subject. The subject we started on last time was to use reductions via computation histories. And so that will make us look at what a Turing machine does and pay even more attention to how the configurations were taking place, and to use that one as part of the thing we will do for reduction. And that one, we called it reduction via computation histories. And so there was a reminder, this was like from last time, except that the last bullet point is now changed to say in last lecture instead of today, because last lecture was the day where this was introduced. And today, our goal is to use this reduction via computation histories to show an undecidable problem. But there was one thing we did last time. The thing we did last time was to use this same technique to show one particular problem that actually was decidable, to some degree, a little bit of a surprise to some, in some ways. So I'm going to have two slides now, just because we are using this computation history as a way, as a part of our reduction. Even though I have given you this slide, even though we have talked about it last time, it just helps to get it back again. And so this is going to be flashing two slides to just have some definitions recalled for us, so that we would go to the business we have today. Let's not forget what we want to do today. We want to add one more thing to our toolbar: reduction via computation history, to show even more problems that are undecidable. And so until we get to the place where we show one more problem that is undecidable, we will not call our job done. So we'll do that. So let's define, or recall the definition of computation history. We've got a Turing machine M, input string W. We call an accepting computation history for M, the Turing machine, and this string W, it's the sequence of configurations, one after another, C1, C2, up to CL, where C1 is the start configuration on this input string, and CL is an accepting configuration. We call that an accepting computation history. If the last one is a rejecting state, then we call it a rejecting computation history. The only thing I left in between is that when we have this C1, C2, and so on, each CI is going to legally follow from the preceding one. This is more like what the transition diagram, the equivalent of it, would have done for a Turing machine. So this is what computation history means. So we've got these configurations sequenced, and we have that history starting from the start configuration and ending with either an accepting or a rejecting history. When it is accepting, we call the entire history accepting computation history. When it is rejecting, we call it rejecting computation history. Definition. We needed this one to come up with a Turing machine that has got a restriction on memory. And we call that one a linear bounded automaton, to show its distinction from a standard Turing machine. And so we kind of define this one using the head of the Turing machine, that it is not allowed to go past the right. Another very quick mental picture for it was to say what you see on this picture now. Our Turing machine, when we first learned it in week 1, after we came back from spring break, the second lecture or the third lecture, we drew a diagram like this, except that we did make the tape infinitely long. It was unbounded. Now we're dealing with one that is bounded. That is probably good enough of a definition. And it is called linear bounded automaton because we can think of this Turing machine now to say a linear bound on the input size. And so the memory that we have available now is going to be twice, 3 times, 5 times that input size. If you think of it like a program, you would say, for example, if you were going to swap things and so on, so somebody gives you an array of lengths 10, you could have a memory fixed for that one and you don't have any more room. But if you allow yourself twice as many, then maybe you can have some variables that you could use to swap things and so on. So you could use twice the space. So in this this sense, we have got a linear bounded automaton that you're working with compared to what the input size would have been, unlike the standard Turing machine where your memory is unbounded. And so what difference would it make when the Turing machine is now linearly bounded automaton? And so we saw one language, and that language was about acceptance. And we called that one ALBA. And so the language there was, we've got an encoding of the Turing machine M and the input string W, and it accepts the string W. That language is what we called ALBA. And we came up with a result on it that says this language, unlike its Turing machine counterpart, that's called ATM, which was undecidable. This one is decidable. And the way we showed that one was using these computation histories. And then there was an intermediate result that I called a lemma, and that was to kind of give quantitative relationship between the input size and how many symbols we have in the alphabet and how many states we have in the Turing machine. And that was a nice number that's a product of three things, the three things I just told you. And the crucial idea there was the reason that ATM is undecidable in the first place is because we don't know whether the machine is going to run forever, loop forever, or terminate. And we found a way to know when it loops forever, and it is when it repeats a configuration. So if it comes for one configuration another time during its computation, when we look at its computation history, then we would know, okay, now this machine is never going to end because it is repeating a configuration, and that happens when it loops forever. If we are able now then to know how many configurations we have, which we have here, then we will know whether that machine is going to halt or not, and that's why this one is decidable. So we had a couple of slides giving a proof for lemma, give a proof for the proof that I'm not going to do. See, these are repetitions from last time, and the proof was there last time, so we don't need to repeat. What we do instead today is job number one. Our goal for today is to see one more, if we can also two more problems that are undecidable, and here we go, we have. And so that same Turing machine with restricted memory, linearly bounded automaton LBA, when the language is about to decide whether it's empty instead of accepting, then now we have an undecidable problem. So here we have the language definition, ELBA is what we'd call it, and the result we have on it is that it is undecidable. And so bear with me now. Here is a place where you will be patient with me. I'm going to go through slides now that would prove this. And so we'll do the proof idea, and so we'll have lots of texts, okay? But the point of those slides is to help you. So when you come back and look at them, you've got a complete description. So don't get too much. If you are a note taker, then this will be a place where you will be selective in how many things you would want to write. But follow me along, because it's going to be kind of difficult if you do not follow me in one slide, because I'm going to continue the argument in the next slide. What are we doing? We are doing that this language is undecidable. We are going to show this. And so we'll start with the proof idea and then come clean with one slide where we have our nice table that says, here is a Turing machine that does the job. Okay. The proof idea, just like any proof that is around reduction, is going to start from an undecidable problem. And so we're going to reduce it to ELBA, okay? And the choice we have made, and this is commenting, as we have seen, we're going to reduce it from ATM. So start with ATM, it's a reduction from ATM, and we'll show that if ELBA, our investigation now, our character that we are looking whether they are decidable or not is ELBA, and we will show that if this were decidable, then ATM would also have been decidable, and therefore we will arrive at a contradiction. So when this is finished, after these slides that we go through, the last sentence should say, thus, there is a contradiction, and therefore this cannot happen. That's how it will end. So suppose now we will start, for the purpose of contradiction, this ELBA is decidable. So what we are going to do, the rest of the business now, will be to use this assumption to decide ATM. How can we construct that machine? So for a Turing machine M and an input W, which is what our ELBA would take in. So for a Turing machine M and an input W, we can determine whether M accepts W by constructing, this time now we are going to focus on an LBA, and we'll give it a name, we'll call it B, by constructing a certain LBA B, and then testing whether LB is empty, right? That's what the language is. LB is empty is the language. So the language that B recognizes, the one that we just described now, comprises all accepting computation histories for M1W. This is a play on words now. So this should be self-evident. The language that B recognizes comprises all accepting computation, because it recognized them, of course, accepting computation histories for M on W, because these computation histories are a function of what the input is, and therefore without the for M on W part, this sentence will not be so very meaningful, right? So the language that B recognizes comprises all accepting computation histories for M on W. Now we are going to argue. If M accepts W, this language contains at least one string, and therefore it's not empty. If M does not accept W, this language is empty. So if we can't determine whether B's language is empty, clearly we can determine whether M accepts on W. So we have now tied what this construction of B with what it means M accepting W or not. When it accepts, the language is non-empty. When it does not accept, the language is empty. So the two would become equivalent. This is how we are developing our idea. So bear with me. We have talked about and argued for an LBA-B and its relationship with how the Turing machine M would be relative to accepting W or not. And so we have established that. So now we are going to construct B from M and W. And we need to show more than the mere existence of B. What do we want to do? We have to show that the Turing machine can obtain a description of B given the description of M and W. That's our reduction. That's how we are going to be able to say we can now construct B, because we are given a description of M and W. So we have to show that the Turing machine can do that. I want to remind you a couple of things we have done so far. So far, when we were doing something like this, we would construct this R is what we will use to call them for all of those reductions we have shown from ATM without computation histories, but some other direct way to show the Turing machine that we would do. For that reduction, we used to call it R and R and R, and then we'll see how the simulator would do it, right? So we construct B now only to feed its description into the assumed one, the ELBA decider that we say exists, but not to run B on some input. So this is a technical thing that you need to remind yourself in case you have forgotten it. So all the idea here is to construct this B to only fit its description to the one that we have assumed, but not to run B on some input. Okay, so now we're going to construct this B. We are going to construct B to accept its input X if X is an accepting computation history for M1W. So that's the relationship we made between B and M. So we construct B such that it would accept its input X if X is an accepting computation history for M on W. To be able to do that, we're going to play a little bit of an organization now. So we will assume now, because we are using this computation history, we're going to turn this computation history into one big gigantic string. And so we'll assume now the accepting computation history is presented as one single string with the configurations separated from each other by a symbol. And this symbol happens to be a hash. And so we have now C1, C2, C3. This is the computation history. And so we have one long string made up of these ones, and to know where we begin will be an ending, where one configuration is starting and the other one is ending, we use this symbol to separate them. Okay, so I'm going to trust that you have been following me along so far, and we are in the business of constructing B, and B has now an input that is one string that goes back to looking at what M was doing on input X and all of the configurations that it has. All right, so now let's going to argue for how this LBA B is going to work. And it's going to work in the following way. And so if you have wondered why I have written it this way, there's more things to write, and so there will be more things to come. Okay, so follow me along. So the LBA now works as follows. When it receives an input X, B is supposed to accept if X is an accepting computation history for M and W, for M on the input string W. So to be able to do this, first, B would break up X according to the delimiters into the strings C1, C2, and CL the way I showed you before. That's the first thing it will do. Then B would determine whether the CIs in this breakup satisfy the three conditions of an accepting computation history. And what are those three conditions? This will be a reminder, basically. So when we have this configuration from C1 to CL, we would call this one acceptable. It has come to an accepting computation history if we write if we start at the right place. What is the right place? If C1 is the start configuration for M on W, that should be there first. Then we should make sure that each one of these CI plus ones follow legally from CI. Another way of saying this would have been, if I was really, really consistent with the way I defined them, I should have said CI minus one. All right, CI legally follows from CI minus one is how I have defined it, but this is the same thing, right? So each CI plus one legally follows from CI. That will be condition number 2. The third condition is the last one. CL is in fact an accepting configuration for M. If M checks these 3 and determines, then it would know that it is an accepting history. When it has done this one, what we have now established is that B will know when M accepts W. What our goal is, don't forget, and I won't blame you if you forget it, was the language that we were working with was about empty, in fact. And therefore, we have to invert this answer we get to positively answer our question on LBA. So by inverting the decider's answer, we answer the question to whether M accepts W. Otherwise, we would have, so it would be, if it is non-empty, it will accept. If it is empty, it will not accept. Because our question is to determine whether it was empty, then we have to give the negation of this answer, is what the second point says. After we have done this, finished, if this was done, then we will argue that ATM would have been decidable if B, the decider like this could be obtained, but we know that ATM is undecidable and therefore this B is undecidable. So this completes the proof idea. The only thing I haven't told you in detail is how B would check the first one, that C1 is the start configuration, how it would check whether one follows from the other one is in a legal way, and whether the last one is an accepting configuration. There is a little bit of a paragraph of a discussion in the book if you want to go back and check them. But the point there is all very, very technical and low level. The point is we can check these things and verify, and B can do it. And after all of this, the whole point is to show that we're not going to construct this one. As you know, we are showing that this is undecidable. We have successfully shown that ATM can be reduced to B, and B is therefore undecidable, and therefore we have the ELBA, our language that we wanted to show to be undecidable. The proof idea is now complete after a walk of 3 or 4 slides of argument. What we will want to do now is put them in one slide, and that's exactly what the next slide will do. We put it together, and the way CptS calls it, we call it a proof at that point. So far, it has been a proof idea. So here is the complete proof. We are now ready to state the reduction of ATM to ELBA. So suppose that we have a Turing machine R that decides ELBA. We construct our simulator Turing machine M to decide ATM in the following way. We take the input encoding of M and W, where M is the Turing machine and W is the string. We construct step number 1, construct LBA B from M and W as described in the proof idea. What was that? That was slide 11 to 14, 4 slides, and you were patient working with me on that one. So that was point 1. Point 2, we run R on input B, and if R rejects, we do the opposite, we accept. If R accepts, we reject, and you know why that is then. So this is the complete proof. And then there is a little bit of a discussion about this one that would kind of complete it, because this is just a proof, and we have to argue that the existence of a B would now make ATM decidable, and therefore we will arrive at a contradiction, and therefore ELBA is undecidable. And so that is formal statements around that is shown here. But there is a nice picture also that I wanted to leave you with to see how these configurations and when they are delimited by X looks like. And so that's the discussion that you see on the black box here. So the proof of that theorem, when it is complete, is in the green box. And what you see on the black box is an elaboration on it and the final statement that this would lead into a contradiction, and the figure that illustrates how these configurations are showing. So if we read it together, so if R accepts B, the encoding of B, then LB would be empty. That's now a build-up for why we are rejecting when we accept in step 3 and accepting when R rejects. That's the formal statement. Maybe I shouldn't be reading it because it's basically going to repeat that. What I really wanted you to have a look, not necessarily just now, but also later on, is to see how these delimited configurations look like on a tape, and our LBA, the one that has got limited memory, now looks like. That's what the name B you see on the control is. And here's how the tape looks like. And so we have done what we wanted to do with LBA. We showed that it is undecidable, and we used a reduction that makes use of computation histories. Basically, that's what we wanted to do. So I want to give you one more result because we are busy. We wanted to do how many things can we show undecidable? So we did add one, and that was ELBA, but we can add another one. And this another one is something that we will call Allcfg. So the LBA was the limited memory version of Turing machines, but we can also do something like context-free grammars where we're given a grammar that is context-free grammar, is it empty? And we have talked about this one indirectly at some point, but this problem is undecidable. The good thing is what we've just learned about having to use computation histories could be used to prove a result like this. For the purpose we have for this course, I am very happy if you just know the result, that Allcfg, that's this language, the language that you see right in front of you now, is undecidable. And the way to prove it is using reductions that use computation histories. I don't necessarily think that it would be worth our time now to go in detail and see how reduction using via computation histories can be applied to this one. It's very similar to what we just did, but it will not be necessary for us to go through that again and to see that. The result, of course, is important, and I want you to remember to know the results. And so we state this result without proof, and it suffices for our purposes. That is what I wanted to say on this slide. So I want to come back and look at our growing list as we conclude now. And so we've got 5 minutes or so, and I want to spend some time. So we grew. I mean, we did a good job growing this undecidable list of problems. We started with ATM and added and added and added. And today we added two. We added ELBA, the emptiness language, when the Turing machine is reduced to linear bounded automaton, and that turned out to be undecidable. Unlike ALBA, look at the left. So on the left, we have ALBA added also to the decidable list, although we didn't intend to do that. We did do that when that problem is reduced to Turing machines with limited memory, LBA, that problem is decidable. So we added one and we added two here. And what I also wanted to remind you with this picture here is what we used as a technique to show. For ATM, diagonalization. For everything else was reduction. Most of the time we reduced from ATM. A couple times when we showed EQTM, we used another problem that we knew was undecidable. ETM, in our case, in that particular discussion, was used. And this could be true. Next time you will see more times in the future or whatever in this course, maybe not so very much left to do now, but whenever you have to show an undecidable problem, you can start with a known undecidable problem and successfully reduce it to the problem that you are investigating. And that now, because we have a large collection, gets easier because there may be some problems that are quite similar to these ones where the reduction would make sense, just like we used EQTM to show, we used ETM to show that EQTM was undecidable. And the last one were added to show still reduction, but we used computation histories. And that's what our topic today was. And the yellowish kind of language that I showed you there were not shown in any of the lectures we covered, but we kind of relied on a result due to Rice that says we could show the same way as we had done for regular TM, that it is undecidable. And he generalized this one to say language properties are undecidable, is the essence of it. And so you would be well aware, would be worthwhile to know that result. But this is where I want to stop today, and this is a great place to stop. We are in chapter 5 in the book, and if you kind of follow along or you read ahead, what we did do is in section 5.1. There is a section on 5.2 that will not be needed as part of this course. But on Monday, I want to talk about reducibility still, but as a mapping function, and that is in section 5.3. And I'm hoping that one lecture would be enough for what I want to draw out of it for the purpose of this course, but it is a very, very nice transition to what we want to do next. What we want to do next is going to talk about intractability, something that would take us a little bit of an introduction to complexity theory, and we'll spend a couple lectures on that topic. And those two topics, reducibility as a mapping reducibility, that function to compute them, and what we use in complexity theory to talk about intractability are related. And so that will be a good gateway to get to that point. That is week 5 that I'm looking ahead to. And week 6 will be mostly about review of the course and getting ready for our finals. Okay, this is what I want to stop. Let me see if you have any questions for me. Anybody else got any questions? Everything was clear? Okay. Okay, so if you do not have any questions, this will be a good place to stop. I'm going to make the recordings available when it is ready. Make sure that you check them out every now and then when you get a chance, and especially now that you have homework to do. For the homework that I have pointed out where lectures are important, you can go back and look at them when you solve. Use the office hours next week. James is worried that he hasn't heard from you about homework 7, so don't make him worry too much. So ask him questions if you have on homework 7, and use the office hours then, and aim to finish early. That's what I told you last time. So if you do not have any questions, I don't mind letting you go a couple minutes early today. That will be a well-deserved one for what you've done, and being that it is a Friday. So if you don't have any questions, then I'm going to stop here. I'll see you on Monday, and have a great weekend. And I'll report on your you're telling me of your stories about your walking habits on the time we're in. Okay? Take care. See you next time.